All right, welcome back. I want to start off immediately by doing another example that I wanted you guys to try. Can we do that? Start off with you guys trying something? I hope you remember what we were doing last time. Maybe I'll just real quickly refresh our memory about showing that something, a sequence converges to something. So the example we did last time was so this is, oops, not that. Two plus 1 over root n, this was the example that we did at the end last time, converges to 2. This is actually another way of writing convergence that our book often does with the arrow like that. So that is a synonym of lim 2 plus 1 over root n equals 2, right? This one, I would like, this is from last time. I don't think we need to go over it. You've all got it on in your notes right there. Yeah, let's try one new one. I would like you all to try to show that the limit as n over n plus 5. Now, last time we did n plus 5 over n. You should be able to see that in your notes. You can copy a lot of that stuff, but it turns out you had to do this one with a slightly different trick in the middle. Can anyone say for now, what's the limit going to be? 1, also 1, yeah. For the same reason that n plus 5 over n has limit 1, this one has also limit 1. All right, I would like to see if you can do it. You should try, for the most part, to copy the format from last time. But you will see something has to be done slightly differently for this one. I'll give you a few moments, and then I'll walk around and see how everybody's doing. Feel free to talk to your neighbors. Great, yeah, right now. Congratulations. it going? Well, this looks pretty good. Uh-huh. Yeah, yeah, yeah. Okay. All right. Yeah, this is really some of the things. You there?
Change the one.
Yeah, yeah. Yeah, that's great. Yep. There's a little hint for the simplifying step. A lot of people came up with this. Some people are still stuck, I think. Try to make a common denominator in order to subtract 1 from that fraction. See what happens. Excellent. Yeah. Okay. That's it.
Yeah. Put it in.
Yeah, yeah. Just fine.
To see if it
Looks like people are doing pretty good. I'm going to write out my version. If you're still going, don't look up if you don't want spoilers. All right, I wrote out my answer. I saw a lot of people work this all out, or were at least on their way to it. So yeah, the work that you do on the side, if you follow my hint, a lot of people didn't need my hint. Some people took my hint gladly. You subtract the fractions, you get -5 on the top, which allows you to actually do away with the absolute value signs. The -5 is negative, and the denominators are automatically positive. So you get 5 over n plus 5 is the same as that absolute value thing. We want to make that less than epsilon. You do a little business here to solve the inequality for n, and it says n greater than 5 over epsilon minus 5. There are some other ways you might have gotten this to look slightly different based on how the steps you did to solve. But anyway, this is what you want to choose your big N. So I say let the big N be greater than 5 over epsilon minus 5. And then let little n be greater or equal to big N, and we have blah, 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 blah. And eventually you get out to epsilon. Are there any questions about that? I hope that this worked out for you all. All right. It's a, there's a lot of structure to it. So hopefully, even if you encounter one of these that you have to do, even if you feel a little lost in the details, hopefully you can follow along with the structure at least as sort of a guide. All right, excellent, great. That was a nice little warm up. There is a few more little details in this section, and then I think we're going to be able to start the next section today. One thing that I want to say is this is a theorem which the book kind of skips the proof, and I thought first I thought we were going to do it. I actually wrote out notes to do the proof, but I think I'd rather skip over it. I think the time is better served doing more examples. So the theorem is about convergence. This is a theorem that you might not even think about if I didn't sort of bring it up, because it seems obvious, but it is really something that it deserves to be proven. It says if you have a sequence an and it converges, then the limit of the sequence is unique. That is, a sequence can only go to one limit. It's not possible to have a sequence which approaches like 2 different things at the same time. If a sequence if you feel like it is approaching 2 different things at the same time, that means it doesn't converge, right? Converge means it only approaches one thing. So if the sequence converges, then the limit is unique. All right, this maybe we'll talk about this more in the future if it comes up, but I think I'm just going to leave it at that. The definition of convergence means that no matter how small the epsilon is, there's always the sequence, its values are eventually within epsilon of the limit point. It's not possible that could happen for 2 different limiting points. You can't be like as close as possible to one number and also as close as possible to some other number. That doesn't make any sense. So this is about convergence. There is only one limit to a converging sequence. There is no such thing as a sequence which converges to 2 different limits. Such a sequence does not converge. All right. The last thing that I wanted to mention from this little section, actually 2 last things, sorry. One is what I will call a topological, I didn't spell it right, topological view of convergence. Topological is a fancy word. Topology is a discipline within mathematics. Actually, my own research area when I do, I do some math research. My training is in topology. When I meet other mathematicians, they say, "Oh, what kind of math do you do?" I say, "Topology." That was a pretty awesome story, wasn't it? Topological. So topology is vague. It's hard to say exactly what it is without too much technicality, but topology is vaguely about sort of shapes of things and mathematical ideas which have to do with points being close together versus points being far apart. So a topological view of these things generally will be characterized by saying, talking about sets of nearby points. That's kind of the basic idea behind what people talk about when they are talking about topology. So you can express the definition of convergence in what I would call a topological viewpoint. So, here's a very simple definition. For some number, a real number, and some epsilon greater than 0, this is called the epsilon neighborhood of A is this set. Our book writes this as V with the sub epsilon of A, and it is the set x in the real numbers such that absolute value x minus A is less than epsilon. It's called the epsilon neighborhood. This over here on the right side, this business, your interpretation of that should be the distance from x to A is less than epsilon, right? So these are all the points which are close to A. How close? Within epsilon, whatever epsilon is, all right? Another way, this set also, if you like to think in terms of intervals, this is the same as the open interval, A minus epsilon, comma, A plus epsilon. All the points which have distance within epsilon of the number A. It is the same as the interval A minus epsilon to A plus epsilon. Or if you like, you could draw the picture of this on the number line. If this is the point A, what I'm talking about is this set right here. The interval of points nearby to A, where the nearness, sort of this little radius, is epsilon. All right, that set is V sub epsilon of A. The neighborhood, the epsilon neighborhood of A. It's all the points nearby within distance epsilon. All right, but anyway, you can phrase the definition of convergence using this epsilon neighborhood as part of it. So here I'll write this as the definition. It's the same definition as what we said before. We say AN converges to A when it's going to look mostly the same. For all epsilon greater than 0, there exists n, a natural number, such that n greater than or equal to big N implies. So here's the only difference. It used to say, the version that we had last time said, what did it say? X minus A less than epsilon, right? Not X, AN minus A less than epsilon, right? But this just means that AN is within distance epsilon of A. In other words, AN is in the epsilon neighborhood around A, right? If I say the distance from AN to A is less than epsilon, that's the same as saying AN is in the epsilon neighborhood around A. AN is in Vn of A. V epsilon of A, right? That's the same as the definition that we had last time. So this is not really very different at all from the way that we discussed it before. But the topological viewpoint would encourage you to think of things becoming close to other things. So one way to say this definition in less formal language is that, oh, microphone off. Okay. In less formal language, we could say something like, beyond some point, by which I mean the big N, all values of the sequence are inside the epsilon neighborhood of A. All right, this is kind of the topological way of saying what the definition of convergence is. If you look in the sequence beyond some point, beyond some big N, all the values of the sequence, all the terms of the sequence are inside the epsilon neighborhood. In topology, we often abbreviate the word neighborhood because it's such a long word as neighborhood. That means neighborhood, all right? Beyond some point, all the terms of the sequence are inside the epsilon neighborhood. Okay, we're not going to make a big deal out of this topological viewpoint right now, but it's going to be sort of a constant companion throughout the semester, and there are times when we are going to make a much bigger deal out of it. So I thought I would mention that at this point, although we're not going to make a big deal out of it at this this point. Any thoughts about that? Questions? All right, one last thing before we move on to the next section, and that is about, we've done many examples of sequence which does converge somewhere, show that this or that converges to this thing. What about showing that a sequence does not converge? So let's talk about divergence, right? A sequence which does not converge, we say it diverges. Can you show that a sequence diverges? So, divergence, this is the opposite of convergence, right? So, let me just write the definition again of converging. So we say AN converges to A means for all n somewhere in 0, there exists n, a natural number, such that n greater than n implies an minus, sorry, I scribbled too much, absolute value an minus a less than epsilon. All right, I'm going to try to write the opposite of that, which is how do you actually show that something diverges? You have to demonstrate that the opposite of this definition holds for the diverging thing. So I'm going to say an does not converge to A. How would you say that logically? This is something that I'm sure you talked about in your discrete math class. If you have a big statement like this with quantifiers in it, anyone remember? How do you say the opposite of that? I want the negation, the logical negation of a statement like that with the quantifiers in it. Anyone remember this? There was some stuff about if you have, for example, if you have a for all and you want to take the opposite of that, what happens? Yeah, when you negate a for all, it turns into a there exists, and when you negate a exist, it turns into a for all. So the negation, if I were to write the negation here, it would say, what? All right, sorry. I'm using the wrong key here. There exists epsilon greater than 0, such that. Then for all, right, the there exists big N needs to become for all big N in the natural numbers. Okay, up here we had such that, and then this implication. Does anyone remember how do you negate implication? I'll try and write this off on the side. What if I have like the negation of P implies Q? You remember that? P, it's not Q implies P. That is called the converse, which is not.
P or not Q, and then you do that.
P implies Q. It's like P or not Q.
Yeah. Right.
Yeah, and then you negate that.
Yeah.
Yeah.
It's not P.
Usually we write it this way: not P and Q, which is what you get if you do what he said. Although I don't usually think of it that way. I think of it, P implies Q means if P is Q, then if P is true, then Q is true, right? The opposite of that would be that P is not true, but Q still is true, right? So that's the. Is that right? No, I got this backwards. Sorry, it should be P and not Q. That's what. P implies Q means if P is true, then Q is true. P and not Q means P is true, but Q is not true. That's the opposite of saying whenever P is Q, then Q is true. So P is true, and Q is not true. Usually the way you think of this is like sometimes, right? P implies Q, you think of like whenever P is true, then Q is true. But the opposite would be sometimes P is true, but Q is not true, right? Those are opposites. So over here, this implication is going to turn into some kind of and. So this says, yeah, for all big N's in the natural numbers, sometimes it is possible that N is greater than or equal to N. So I'll say some N greater than or equal to N. And then with the opposite of that over there, so this would say AN minus A is greater or equal to epsilon, right? This is like P and not Q. So this is what we need to demonstrate if you want to prove that something does not converge. It's a little weird here. And actually later on in the class we're going to learn better ways to show that things do not converge. There's some nice tricks you can use. So we're not going to make a big deal of it at this point. But I thought we should do at least one example. Let me just say the way to think about this is this one I have maybe a slightly easier time thinking about what that means topologically speaking. It means that we can always find terms that are far away from A. Right? The conclusion there with an minus a greater than or equal to epsilon, it means that the term an is not super close to a. It's far away. Maybe not super far, but it is further away than epsilon. Where, remember, this epsilon is a there exists. So there's a specific distance where every so often one of the values is farther away than that distance. All right? Let's see if we can just do one example. Like I said, we're going to come back to this with some better theorems that allow us to skip a lot of details. But let's just see if we can do, how about, I meant this, an, let's try minus 1 to the power n. So this, the sequence would be minus 1, 1, minus 1, 1, minus 1, etc. All right? This does not converge. Now, in order to say what the definition I just wrote up there says does not converge to a, some specific number. So let's show that, let's sow that an does not converge. Let's just show an does not converge to 0, all right? It's not so hard to show that it doesn't converge. It doesn't converge to anything, really, but if we want to prove that it doesn't converge to something, we got to choose the something that it's not going to converge to, okay? What we need to think about is, can we demonstrate that there is some epsilon so that these numbers are further away from 0 than epsilon? So remember, this definition of does not converge begins with a there exists. So if you're going to show something does not converge, you must begin by saying what the epsilon is. All right? Now, can anybody think of, sorry. Here, I'll draw a picture of this sequence. It's not so hard. I got 1 here, minus 1 here, and all the terms, they just go back and forth. Right? And I have to choose some epsilon so that these terms will be far away from 0, like outside of the neighborhood around 0. Can anyone think of such an epsilon? I want to choose like a neighborhood, say with some epsilon like this, so that the terms will be outside of there. This is not a hard question. What do you think? Yeah, 1/2 I think is a natural choice to make. Actually, any number less than 1 would do, and greater than 0. So I'm going to say let epsilon equal 1/2. And then we need to demonstrate this business that is circled in the blue up there. We have to demonstrate that for any big N, there are always going to be some terms that are far away from 0, further than 1/2. But that's actually easy in this case. So let epsilon equal 1/2, then I can say absolute value an minus a. Of course, in this example, an is minus 1 to the n, so I'll write that. And a is just 0. 0 is the point which the alleged convergence points, we're showing it does not converge, right? Can we demonstrate that this is greater than or equal to epsilon? That's what we would like to conclude from the thing in the blue circle, right? Is that greater than or equal to epsilon? What can we do to simplify here? First of all, I don't care about minus 0, right? That, yeah. Yeah, this is just 1, right? The things in the inside of the absolute value sign here are either 1 or minus 1, and the absolute value either way is just 1. Is that greater than 1/2? Yes, it is. All right, so actually in this case, an minus a, well, really I should say an minus 0 is always greater than 1/2. So it does not converge to 0. right? This is even stronger than we needed. You don't actually need it to be always greater than epsilon. You need to show that for any n, for any big N, there exists little n's bigger than the big N, which are greater than epsilon. But we actually, in this case, it's easy enough. They're always greater than the epsilon. All right, so this is how you show something does not converge. Like I said before, this is not, I don't want to make such a big deal out of this because we're going to come back to this soon enough. Any thoughts about that at this point? All right, great. Let's move on to something a little different in our remaining 15 minutes. The next little section, so this was we're in the beginning of chapter 2. I don't know if you care about the sections in the book. The next little section is a bunch of fun theorems about limits. And actually, some of these are ones that I'm sure you've seen already in a calculus class, although the first one that we do, probably you did not do in a calculus class. The first one concerns sequences which are bounded. We've talked already about bounded sets, sets which are bounded above or bounded below. A bounded sequence is basically the same idea, but just for the sake of being explicit here, let's write the definition of a sequence being bounded. We say a sequence, look at this. Okay, a sequence is bounded. So actually in our book, they don't say bounded above or bounded below for sequences. They just say bounded, which means both above and below. But a sequence is bounded. Sorry, I'm talking about a sequence that I'll call AN. It means that there's an upper bound and a lower bound, but actually there's a cuter way that you can say both at once. I'm going to say it like this. If there is some big M, a real number, actually a positive number, such that absolute value AN less than big M for all N. So this means that it will be bounded above and below. It's bounded above by big M, and it's bounded below by negative big M. That's because I put the absolute values right here. This is the trick to get you above and below at the same time. All right. Another way of saying this, I'll just say IE. Equivalently, you can just say that AN, this is, I guess, slightly more topological, is in the interval minus M to M. That's the same as saying the absolute value of AN is less than or equal to big M. Again, for all N. So bounded means that the values, the terms in the sequence, they exist inside a closed interval. They don't go all the way out to plus infinity or all the way back to minus infinity, or both, I suppose. All right, this is what it means for a sequence to be bounded. And the first of our theorems about limits, and probably the only one we're going to get to today, is if a sequence AN converges to A, then AN is bounded. If the sequence converges, it must be bounded. All right? This is something, if you think for a moment, probably you will agree that this is true. I'm going to try and sort of draw a little diagram. I don't know how helpful this would be, but let's imagine I have our sequence AN, and it does converge to A, which means it might do some stuff at the beginning, like maybe here's A1, A2. Just because it converges to A doesn't mean the values immediately go to A. It could be that A3 goes like out here. Maybe A4 goes over here. A5 goes over here. It could do a bunch of weird stuff at the beginning, but eventually the values must do like this, right? Get very close to the A, all right? Even though towards the beginning it could do some other weird stuff, all right? Is anybody convinced that the sequence must be bounded in this case? The idea of the proof is you sort of think about the beginning as separate from the end of the sequence. Like definitely the end of the sequence has to be all right near A. So the end of the sequence definitely cannot go out to infinity, right? What about the beginning of the sequence? Is it possible that the sequence starts out by going to infinity but then it eventually comes back to A. Any thoughts about that? At the beginning of the sequence, it goes out to infinity, and then it comes back again, and eventually converges. Can you think of an example of a sequence that does that? Goes out to infinity, but then comes back and like goes to 0 or something? The answer is no. You cannot think of a sequence that does that because that's not possible. You can't, in a sequence, you can't go out to infinity and then come back. There's no coming back from that, right? Because it takes you forever to get to infinity in the first place. So there's no such thing as a sequence which goes to infinity and then after a few steps comes back and converges to some specific number. That's not possible. But that actually is what we're trying to prove here, right? But that's the idea. You can't go out to infinity and then come back from infinity, right? That's the nature of a sequence and infinity. All right, let's see if we can do this proof. The ideas of the proof here will be helpful to us going forward. So we assume that our assumption in this theorem is that AN converges to A, right? So I'm going to start by saying, let's say AN converges to A, all right? What that means is for all epsilon greater than 0, blah, 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 blah. Lots of stuff about for all epsilons. Convergence is, here's something that we're going to encounter a lot more of in the future. Convergence means something is true for every epsilon. So because of this, I can choose any epsilon I want and say all that stuff about what the convergence means, because the convergence says for any epsilon, all this stuff is true, right? So we can choose any epsilon we like. I'm going to say let epsilon equal 1. Then the definition of convergence says there exists some big N, a natural number, such that n greater than or equal to the big N implies AN minus A less than 1, right? I use 1 in the definition of convergence. Now, there's actually nothing special about using 1 in this proof. You can do this using any constant, but we might as well use 1. So what this means is, like I said on this sort of picture here, the sequence might do some weird stuff at the beginning, but after a certain point, it has to be very close to A. Okay, so what this means is for terms A sub big N and later, all terms are within 1 of the limit of A, right? All the terms beyond this point, A sub big N, are close to A, right? Within 1 of it. Another way we could say that is, i.e., if N is greater than or equal to the big N, then check this out. The absolute value AN is less than the absolute value A plus 1. If all these numbers are positive, then all I'm saying is that AN is like less than A plus 1, because if A is where they're converging to and they're all within 1 of A, then they will be less than A plus 1 and greater than A minus 1. Although I want to talk about absolute values, so if you want to say that properly, allowing for the little a to perhaps be negative, this is the way you have to say it. The AN in absolute value is less than the absolute value of A plus 1. So these ones are bounded, right? Bounded, remember, means that absolute value AN has to be less than some specific value. And these ones are. All of these ones are less than this specific number, big A, or not big A, there's no big A, absolute value A plus 1, all right? So this part of the sequence is bounded. What about the beginning part? This is like the end part, right? When for the terms that are past big N. What about the beginning part? Well, the beginning part is automatically bounded because there's only finitely many of them. There's A1, A2, A3 up to A big N minus 1, the one before that. But those can't go to infinity because there's only n of them, right? There's not enough for them to be unbounded either. So these are bounded. Can I just say the others are only A1, A2, A3, blah, 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 up to A big N minus 1. And these must be bounded because there's only finitely many of them. So there's just one of those is the biggest, and that's it. That one is the biggest, right? These are bounded because there are only finitely many. Only finitely many. I hope you, this says these are bounded. I had a good friend when I first started teaching tell me that my handwriting was too bad. I needed to improve my handwriting. I think of him every time I write something that's hard to read. And this is a true story. I just found out yesterday that he died of the coronavirus. Yep. That was a good story until then. Yeah. It's a shame. He was much older than me, but yeah, he's the first person that I know, like personally, who got the COVID. Rest in peace, Gene. Okay, so can I just say the conclusion here? We're pretty much done here. We've demonstrated that for the terms close to the end, they're all bounded by absolute value A plus 1. And the ones at the beginning, they're bounded just by whichever one is the biggest. So it is a fact that for any n, we always have an, and this will look a little strange, but this is actually another thing that we're going to be writing from time to time. Less than, I'll say less than or equal, the maximum of these numbers, A1, A2, blah, 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 A big N minus 1, or absolute value A minus 1. Whichever one of those is the biggest of all, we are guaranteed that every term in the sequence is less than all of those, right? All the ones at the end are less than this one, absolute value A minus 1. And all the ones at the beginning, they must be less than one of these, just whichever one is the biggest. And so overall, everything in the sequence is less than whatever is the biggest out of all of these. All right? This is a common thing that we'll see at, when you're trying to choose some number which satisfies a bunch of stuff. Oftentimes, we're going to use the maximum of some stuff. All right? And that is the end of this little proof. Any thoughts about that? All right, we got 5 minutes. Maybe I'll just give you a little intro to, I said we were going to talk about some theorems about limits that you definitely will recognize from a calculus class. Maybe I'll just write the statements here, and we'll talk about them next time. So these are, in a calculus class, I might call these limit rules for doing limits. I'll write this as a theorem. If we have two sequences that converge, AN goes to A and BN goes to B, and let's say C is any real number, then this theorem has four parts to it. The first is that the limit of a constant times a sequence, this is C times AN. Anybody remember rules like this? What do you get when you have the limit of a constant times a sequence? Can you do something with that constant? Yeah, you can take it out of the limit, right? The way I'm going to write this is just like that. C times A. I don't know if you were expecting to write C lim AN. Sure, but then lim AN, I said up at the top, that AN converges to A. So this is the same. C times A. Anyone remember any other rules like this? I'm sure whenever you talked about this, you probably talked about some closely related things. Want to shout them out? In our remaining 3 minutes. Here's a hint. I said in the theorem that some of these are going to involve two different sequences, ANs and BNs. What can you say about the limit of two different sequences? Yeah, how about the limit of AN plus BN? I'm sure you talked about this in some calculus class. What do you get? A plus B in this case. It's the limit of AN plus the limit of BN, right? It is A plus B. This, by the way, is the reason, for instance, when you take the derivative of two things added together, you can just do the derivative of each of the two things. Because the derivative is some kind of limit. And the limit adds up nicely when you have two things like that. Okay, what else? I'll just tell you the other three. You don't seem to be wanting to remember. Here's something you cannot do with the derivative, but it does work with just a limit by itself. The limit of the product, AN times BN, is indeed equal to A times B. And one last thing is about quotients. The limit of AN divided by BN. And this, again, is equal to what you want it to be. No funny business here. A divided by B. Although there is a little caveat. There's a slight restriction here when, anyone know what I'm going to say? Yeah, when B is not 0. If B is 0, then actually you can't do this limit. That's not true. When B is 0, sometimes the limit does exist, sometimes it doesn't, and you have to do some more work to figure that out. All right, let's start next time with these. We're going to talk some of them. All right, have a good weekend.